Hello guys, my name is Patrick Mensah, and today I will be talking about how to do some basic calculations in R. So R console is a calculator, so it helps you to do the basic calculations. Now let's start. So if you want to find the log of 56 divided by 0.8.3, you just type the log in this function and then it's going to give you the answer. So the answer is already here. Now, each line can contain at most 8,192. So you can do whatever thing you want to do on each line. So let's look at what the addition of this can also produce. So with this, it gives us this value. Now, two or more expressions can be placed in a single line as long as they are separated by a semicolon. So with this, you can see that all of this are separated by a semicolon, and then it's going to give you a solution on a single line. So let's look at this. This gives you a line, all these lines, and then so far as you use the semicolon, this is the values that it's going to give. So for large numbers, R uses exponents. So for example, 1.8 e to the power 5 is going to give you. Let's look at what it's going to give you. So it's going to give you 180,000. So this is because the E5 means that we move the decimal point 5 places to the right. How about if it is negative? So if it is negative, let's look at what it's going to give us. It gave us 0.00015. This is just because the E4 means that we move the decimal point 4 places to the left. Now, we know complex variables. So in complex variables, we have the real part and then the imaginary part. And then we also know that the I is equal to the square root of -1. So when you look at something like this, 6.9 plus 8.5i, this is a complex variable where the real part is 6.9 and the imaginary part is 8.5. where I represent the square root of 0.1, as I've already said. So let's run this, and this gives us the value. Now you see that in complex variables, we know we have to find the real parts and then the imaginary parts. So let's assume that we give it a value of z, because in complex variables we mostly use z for that. So this is it. Now, if you want to find the real parts, R has a function called RE function, and then it's going to give you the value, which is 7.8 with this. And then if you want to find the imaginary parts, you use this function, and then it's going to give you the imaginary parts. So what is going to be the imaginary parts? The imaginary part of this is -6i. Now, if you want to find the modulus, so the modulus means that the distance from z to 0 in complex plane by Pythagoras, assuming that x is the real part and the y is the imaginary part. So we look at this. So if you want to find the modulus, we know that the modulus is the square root of x squared plus y squared. You see, it's going to give you a very long distance. So we have a function in R that's called mod z, and then it's going to give you the value. So this one, the 9.48072 is the square root of x squared plus y squared. So that is it. If you want to find the argument, you see the argument has a very this equation. There is no need to work on this. R is going to give you the solution. So you just find you just use the argument function, and it's going to give you the value. Now, if you want to find the conjugate, you see in complex variables, the conjugate is all about changing the sign of the imaginary part. So here, the sign of the imaginary part is negative. So let's look at what it's going to give us. So you see that it gave us 7.8 plus. So that is how it is. So now we look at the membership. The membership is to determine if the equation is a complex variable or not. So let's look at it. Is z a complex variable? Yes or no? See, it tells you yes, because it gives you the real parts, the imaginary parts. Now, let's look at the coercion. The coercion is the x function. So if you do that, it means you are forcing any value to be a complex variable. So for example, we have 4.9 over here. If you want to force 4.9 to a complex variable, then it means that we need to add, this is just the real part. So it means that R is going to add the imaginary part to it. Let's look at what it's going to give us. And give us 0i. So that is the imaginary parts that it produces. So now let's look at how to run numbers in R. You see, example. So you see in discrete mathematics. So we have the floor, we have the ceiling, and the floor is the top of the. It means the greatest integer less than a function. Like like if you have 4.8, what is going to be the floor? And then if you have the same number, what is going to be the ceiling? So it means that the next integer at the top, and then it's called a floor, and then the next integer below that value is the ceiling. So let's look at what this is going to give us. 4.8, the floor of 4.8 is going to give us 4, and then the ceiling is the top. Let's look at that, what is going to give us. So the ceiling is the top. So the top is also produces 5. So it's just like, like running the number, like, but this is not running. So let's look at it. So now you can create a function for this. You can also create a function for this by running it to the nearest integer by adding 0.5 to the number, then using the floor. This is an example. I created a function for that. So if you create a function for this, you get this. So now let's say we are running 4.8. So that one 4.8 is going to give you 5. If you run 2.1, automatically it tells you that it's going to give you 2, just because 1 is below 5. So that is how it's going to be. Now let's look at rounding negative numbers. So you see that in negative numbers, -2 is greater than -3. So if you are doing the ceiling, you have to remember that negative numbers mean that you are running towards 0. So let's look at what 3.7 is going to give us. 3.7 gave us 3. People would think that it's supposed to give us 4, but no, because we are running towards 0 when we are using the ceiling, that is how it's supposed to give us. Let's look at -4.4. -4.4 also give us -4, just because we are running towards 0. Now with the floor, we have to know that we are running away from 0. So let's look at the floor of -3.7. -3.7, because we are running away from 0, it gave us -4, and then -4.4 also produces -5. This is just because we are running away from 0. Okay, so that is basically that. Now we use if you want to strip the decimal part, we use the trunk function. So for example, 45.77. If you want to remove the decimal part, we use the trunk function, and it's going to take off the 77. So let's look at it. So it took it off. 4.9 is going to give us automatically 4. Now let's look at how we use the round function. Now the round function is where we round numbers. So now let's look at this. We run 5.6 into the digits of 0. Let's look at what it's going to give us. It's 6. If you run 5.6, it's supposed to give you 6. Let's look at this one too. If you run 6.8, it's supposed to give you 7. Let's run 74.2. What is going to give us? It's going to give us 74. How about -75? it's going to give us negative 75 just because the 4 is below 0.5. Now, let's look at this significant figures. Now, we want to use significant figures. So, for example, when they give you a number, you have to know that significant figures is different from running. Running a number is different from significant figures. So when they give you something like the whole of these figures, and they want you to run it in 7 decimal places, R can give you the solution. That is the solution over here. This is the same as this. The same answer is supposed to give you over here. Now, if you want it in 6 significant values, you get this. So now, let's do some arithmetic. So the screen prompt is already a calculator, and you have to remember that R also uses board mass. So if R is using a board mass, when we have this equation, you should know what it's supposed to do. It's supposed to do bracket of division, multiplication, addition, and subtraction. So R is also doing that. And then you have to also remember that the power, if you want to do the power, R uses the correct symbol. So if 2 raised to the power 5 or 3 raised to the power 5, it's going to be 3 caret 5. And then remember, we are also using the board mass. So this is what it's supposed to give you. Now, when you want to look, let's look at how you do the log function. The log function gives logs to the base e, and then the e is 2.718282, for which the antilog is exponent. So for example, the log 10, if you want to use log 10, we use this function log 10, and this is what it's supposed to give us. Now, if you want to find the antilog of this, we use the exponent. So the exponent, so ESP2 is going to give you the antilog of log 2, which is this. Now you see the old fraction, the old fraction, like for example, log 3 to the base 10. So log 3 to the base 10, you can also do that, and it will give you an answer. Log to the other bases are also possible. For example, log 7 to the base 4. That one is also feasible. You can do that. Now let's look at square roots. Square root of 9. We have a function for that. Square root of 9. And you know square root of 9 is 3. Factorial. We also have a factorial function. The factorial function of factorial of 7. Factorial of 7 will give you this value. Now let's look at the binomial coefficients. We know the binomial formula, but so many formulas. I mean, it's not difficult though, but it's very easy for R to do that. So let's 6 chooses 2. Very simple. So you do that and it gives you the value. Now let's look at this. When you want to generate a random numbers between 0 and 1 from a uniform distribution, we use the run if function. And then the run if function, if you don't do anything to it, it's just going to generate this one, the end value. So here we see 7 here. So the 7 means that we are going to generate 7 random numbers between 0 and then 1 from the uniform distribution. So when we run this, we get 7 numbers, random numbers between 0 and 1. You can also change the minimum values and then the maximum values. So for instance, this one is going to give you 50 random numbers where the minimum is 1 and then the maximum is 100. So let's look at it. This have generated all these things. We will talk about this as time goes on when we want to generate our own values and then find correlations and stuff. So let's look at the cos, the sine, the cosine, the tangent function of x in radian. So sine 90 will give you this, and then cos 90 actually is not 0, but people think it's 0. So cos 90 is really not 0, but just that we just run it. That is why. So cos 90 is minus 0.44808736. But however, the issue is that we just run it. If you round it, that is where it gives you 0. That's why they say people say cos 90 is equal to 0, but basically cos 90 is not 0. So tan 90 will give you this. Time 45 will give you this. Now we look at the inverse trigonometric transformation of real or complex numbers. So this one too, we use the a cos, the a sine, the a tan, the functions, and it also produces the answers. So when you look at the inverse hyperbolic trigonometric function of real or complex numbers, we also use the following functions, and then they give you all the so if you see this INF, it means that the answer is infinity. So that is basically that. Now when we want to find the absolute value means that we are taking the negative sign off. So the absolute value, we use the ABS function, that is absolute value function. So absolute value of negative 199 is supposed to give you 199 by just taking the negative sign off. And then with this absolute value of 45, it's the same 45 because there is no sign. Now we look at pi. There is a pi also for that, a function for that. There is also a function for pi. So pi is 3.141, blah, 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 blah. The sign, you can do sine pi over 3, which will give you this, cos pi over 3, this. All of this, I think they can give you answer. Now let's look at modulus and then integer quotients. Now, the integer quotient uses this sign, and then the remainders also uses this. So for example, if you want to find how many 11s can be found in 135, this is how many 11s can be found in 135. So if you run this, you can see that we can find 12 11s in 135, but it didn't tell you the remainder. So if you want to know the remainder, that is what we call the modulus function, and the modulo uses the double percentage sign. So if you want to find the remainder, so that is the modulus. So you can see that 11 go into 135 12 times and then remainder 3. So the remainder is the modulus. So modulus are very important to determine if a number is even or odd. Odd numbers have modulo 2 value 1, and even numbers have modulo 2 value 0. So let's say 12. If you want to find, if you want to check whether 12 is a modulo 2, we just use this function and see. You see that it gave you 0. So it tells you that it's an odd number. Sorry, an even number. And then if you get 1, it means that it is an even an odd number. So with 55, you can see that when you do that, it gives you 1. So it tells you that 55 is an odd number. So now, if you want to test if a number is an exact multiple of this other number. So for example, if you want to find if this value is a multiple of 8. So now what we have to do is that we find this and we use this function. If you use this function and then this tells you that if you find the modulus of this, the answer is supposed to give you 0. So this is just like asking the question if it is yes or no. So if you do that and it tells you that false, then it means that this number cannot divide. This number cannot divide 8. Cannot be divided by 8 exactly. So let's look at this one too. If you divide this by this, are you going to get 0? If you get it, then it means that it's the exact multiple of that number. So let's look at this one too. We do that and then it gives you a true value. Then it means that 625872 can be divided by 8. So that is how it is done. Now let's look at how we use variables and then we assign values in R. So there are 3 important things to remember when selecting names for your variable. 1, the variable names are case sensitive. For example, if you use X, X is not the same as capital X. if you use small x, you have to refer x everywhere with a small x. If you use capital X, it's not going to give you the same thing. Number two, variable names should not begin with numbers or symbols. So, for example, if you use 2y, no, it's not good to do that. And then at x, no, it is not. All of these are not very good to do them when assigning variables. You don't have to do that. And then variable names should not also contain spaces. So, like for example, you can use part men and not part space m, men. And when you do that, that is not also it's not acceptable. And another thing that you can also do is that you don't have to assign variable names with like a very huge name and so many other stuff, so that you wouldn't be having problems calling the numbers and stuff. Just use some simple things and then you just assign it. For example, x is equal to 100. You just use this, and this is the sign to do that. There is another sign to do that, but I think this is the most commonest value to do that. So you do this, and then you call the x, it tells you 100. We have to know that this is not the same. This one, you see, this one, there is a space over here. This one is not the same. Note that there is a space sign between the less than and the minus sign. This asks a question whether it's telling you, this is asking whether s is less than 100 when you do this. So let's look at this. So it tells you false. So if you are doing the variable assignment, you have to be very careful. You don't use the less than sign and then you give it the space. If you do that, this is not good. And then the operators too, we have the greater than or equal to sign, the greater sign, the less than or equal to, the equal to sign, the not equal to. We also have all of these are operators. This one is the variable assigning numbers. This one is this dollar sign is indexing a list. So for example, if you're using a data frame and then you want to index a list, or you want to select a variable, you can use this dollar sign. And then if you want to create a sequence, you use, like for example, from 0 to 10, you use this sign to create that sequence. Now let's look at how we deal with integers. So we look at this x. This x is giving you some numbers, and these are the numbers. So you want to see whether if this s is an integer. So we use the is integers function to determine. We do that, and it tells you false. So it tells you that these numbers are not integers. So let's see whether it's numeric. We do that, it tells us true. So it means that the numbers are numeric. Now let's look at converting them into integers. So if we have x is equal to this, we use this as the as integer function to just convert, or to just coerce, or to force them to be an integer. And then if you do that, now let's see whether it is an integer. So you see that this has been able to be converted into an integer. Now the integer function also works as trunc when applied to real numbers, and it removes the imaginary part. So for example, when you do this, and then you want to use the trunc function for this one, the as integers is going to strip off the -8. So let's look at this. So it will take it off. This one to take it off, and then this one is also take the imaginary part. So you can see that there is a warning over here that the imaginary part has been discarded. This is just because the as integer function has been able to take off the imaginary part. I think this is all we need to know about calculations in R. If you have any question, put it in. Don't worry about it. Just put it in the comment section, and then I will find the answer when there is time. Thank you so much for your time.